Welcome to the chemistry class. Today I'll start a new chapter from physical chemistry, that is states of matter, gases and liquids. Physical properties of substance or substances depend upon the state in which the substance exists. Generally, we know that there are three states of matter: solids, liquids and gases. And in this unit, we shall discuss some important aspects of gaseous and liquid state. And in class 12, we will study the solid state. Physical properties of three states of matter differ mainly due to the difference in the intermolecular forces or intermolecular force of attractions. In case of solid, the intermolecular force of attractions are the strongest. In case of liquid, the intermolecular forces of attractions are weaker than those of the solids. And in case of gas, the intermolecular force of attractions are almost negligible. And the intermolecular forces are different types. It may be dipole-dipole interaction, it may be ion-dipole interaction, it may be ion-induced dipole interaction, it may be dipole-induced dipole interaction, or it may be dispersion forces, or we can tell it as London forces. Okay, next we will discuss these forces one by one. Okay, actually these forces are purely electrostatic and thus physical in nature. Okay, the force works in case of ionic bonds and covalent bonds are different. Okay, they are very much strong forces and these forces are weak. And another name we can give to these intermolecular forces is van der Waals forces, because van der Waals, a Dutch chemist who first investigated the origin of these forces. So first is the dipole-dipole interaction. Dipole interactions. In this case or in this type of force, the attraction occurs among the polar molecules. A simple molecule we can think about HCl or HBr, in which the chlorine or bromine is more electronegative, acquires a slightly negatively charged, whereas the hydrogen will acquire some partially positively charged. And the dipole interaction then takes place among the HCl or HBr molecule. If we draw the structure, then you can understand that HCl, in this way we are writing. So this is chlorine is more electronegative, delta negative, delta positive. This one is delta negative, delta positive. So delta negative, delta positive. So here is the between the plus and minus. Okay, delta positive and the force is acting. So these are the dipole-dipole interactions. And these forces are also called Kiesom forces. Kiesom forces. K-E-E-S-O-M. Kiesom forces. Okay, between the polar molecules or among the polar molecules. And the dipole-dipole interaction energy between the stationary polar molecule is proportional to 1 by r to the power cube. Okay, and that between the rotating polar molecule is proportional to 1 by r to the power 6. Now what is the r? R is the distance between the two polar molecules. Hope you can understand. Now next we will give one example, that if you think about the slightly polar NO molecule, that is the nitric oxide molecule, has higher boiling point compared to the non-polar molecules. We can think about the nitrogen molecule, we can think about the oxygen molecule or hydrogen molecule. Hope you can understand. Next, second we will discuss that is the ion dipole interaction. Ion dipole interaction. Now, this is the force or attraction force between an ion and a polar molecule. For example, we can think about the sodium chloride is dissolved in water molecule. So the polar water molecules are attracted towards Na plus, okay, as well as towards Cl minus. This process is also called hydration of ions. Higher the charge density, stronger will be the interaction. On the other hand, if we take carbon tetrachloride molecule, okay, then it is a non-polar, dipole moment 0 and lacks the ability to participate in the ion dipole interaction. So NaCl will be insoluble in CCl4. So what I am telling, that suppose you are dissolving NaCl in water. So water is a high dielectric constant. So this is delta negative, this one is delta positive. Okay, so this we can represent in this way. This one is the negative pole and this one is the positive pole. Now Na will dissociate into Na plus Cl minus. So Na plus will be solvated by the negative end of this water molecule. And the negative part, that means Cl minus, solvated with the positive part of the water molecule. This is the polar water molecules, okay. So in this way it will be solvated, okay. So that is why it is called ion dipole interaction. This one is dipole and this one is ion, okay. Next we will discuss that ion induced dipole interaction. Ion induced dipole interaction. Ion induced dipole interactions. A non-polar molecule may be polarized by the presence of an ion near it. It becomes an induced dipole and the interaction is called ion induced dipole. Okay, you can think about one ion. We can think about NO2 minus, and here we are taking one molecule, that is Br2, bromine. Now what will happen? Here near about this negative charge, here will be delta positive and here will be the delta negative. So in this way, this one will be polarized. For example, in the presence of, this is the nitrite ion, okay, and this bromine molecule, which is a non-polar, gets polarized to delta plus and delta minus, okay, and this is called ion induced dipole interaction. Next we will discuss that dipole induced dipole interaction. Dipole induced dipole interaction. Dipole induced dipole interactions. Okay. Here we have to consider a non-polar molecule. Okay, this non-polar molecule may be polarized, okay, in presence of a polar molecule near about it, okay, thereby making it an induced dipole, and these interaction between them are then called dipole induced dipole interaction. Suppose we can think about a polar molecule. Suppose this is a polar molecule, plus is there, minus is there, this polar molecule, and here also another molecule is there, that is the non-polar molecule. This is the non-polar. Here is nucleus and outside electron is there. Okay. Now what will happen? And this polar molecule will induce. Okay. And this will be, here there will be the negative charge and here there will be the positive charge. Okay. So the existence of these forces first discovered by Debye. Okay, and this is also called Debye forces, and this effect is called induction effect. Hope you can understand. And the last we will discuss that the London forces or dispersion forces. Next is London forces. This is also called dispersion forces. These forces exist between non-polar atoms like inert gas, helium, neon, argon. These also exist between the non-polar molecules also, that is the homonuclear molecules like oxygen, nitrogen, hydrogen, etc. And these are also known as van der Waals forces after the name of the discoverer. And these forces are always attractive, and interaction energy is inversely proportional to the sixth power of the distance between two interactive particles. And this type of forces are called London forces, and this is also called that van der Waals forces. Hope you can understand. Next we will discuss the factors affecting the strength of these London forces. First one is the atomic and molecular size. Next we are discussing the factors. Atomic and molecular size. If the atoms or molecules have larger size, then it should have the larger surface area, and their electron clouds thus becomes diffused and distorted. As a result, these forces become stronger. Argon gas has higher boiling point than the neon gas, which suggests that the presence of stronger attractive force in argon. Second one, we can tell that molecular weight. Higher the molecular weight, higher will be the molecular size and higher will be the surface area. So the forces become stronger. We can think about octane, we can think about nonane, or we can think about hexane. Definitely octane boiling point will be higher compared to the pentane or hexane. Okay. Next is the molecular shape. Molecular shape. In organic chemistry already we have discussed that molecules containing the long chain, okay, certain molecules we can think about that N-pentane or normal pentane, okay, because of the maximum surface area there will be maximum attraction and its boiling point will be high. And if we compare the branch one, that is the neopentane, definitely its boiling point will be less as the surface area is less. So this London force or van der Waals force will be less here. And next we will discuss the temperature. Okay. So definitely if we increase the temperature, so the kinetic energy of the molecule will increase. Okay. If the kinetic energy of the molecule increases, definitely the interactive forces will decrease. But at low temperature, kinetic energy will be low, and if the kinetic energy is low, definitely what will happen? The interactive force will increase. Next we will discuss pressure. If we increase the pressure, the atoms and molecules will come closer and the interaction between them increases. Thus the magnitude of the London force also increases. Next one is the number of electrons. Ions and molecules having larger size have large number of electrons. Longer number of electrons results in greater diffusion of electron clouds and greater will be the polarization. As a result, there is stronger interatomic or intermolecular interactions. The van der Waals forces are much weaker than the ionic and covalent bonds. Okay. Next we will discuss the application in melting and boiling point, and the existence of the van der Waals forces is responsible for bringing the molecules closer, and the boiling point of a liquid or melting point of a solid involves the absorption of heat to overcome the molecular attractions and to pull the molecules apart. And so with the increase of the magnitude of the van der Waals forces, the boiling point and melting point of a substance increases. So if we increase the van der Waals force, definitely the melting point and boiling point will increase. So in this way we have completed the interactive forces present in between molecules. Generally these are the physical forces, okay. They are not chemical forces like covalent bond or ionic bonds. Next, your topic is that gas laws. Gas laws already you have learned in lower classes, till I will discuss. First law was Boyle's law. Okay. All of you know the statement of Boyle's law. At constant temperature, the volume of a given mass of a gas, okay, is inversely proportional to the applied pressure. So mathematical formula or representation with V is proportional to 1 by P, where number of moles of gas or mass of gas is fixed and temperature is also fixed. So from here we can write that V is equal to some proportionally constant by P. So from here we can write PV is equal to K, that PV is equal to constant. Okay. Now at constant temperature, for a given mass of a gas, if the pressure changes from P1 to P2 and the volume changes from V1 to V2, then we can write that P1 V1 is equal to P2 V2. Okay. So from this formula, okay, or mathematical representation, numericals you have to practice. And next we will derive another thing, like the density and pressure relation. That is also very important. Okay, let the mass of the gas is m. Okay, let the mass of the gas is m. Okay, and next the density at pressure P1. At pressure P1 density will be D1, and at pressure P2 the density is D2. Okay, so we know that density is equal to mass by volume. So from here we can write D1 is equal to m by V1 and D2 is equal to m by V2. Now from here we know that P1 by P2 is equal to V2 by V1. Okay, that we know. So from here we will calculate the V2. So from here we will get that V2 is equal to m by D2 and V1 is equal to m by D1. That will be equal to m by D2 and this one is m by D1. Hope you can understand. And from here we can write that P1 by P2 is equal to, that is P1 by P2, you are writing that m by D2 into d1 by L. Okay, so from here we can write that P1 by P2 is equal to d1 by d2. So P1 by d1 is equal to P2 by d2. That we can write. Okay, so from here we can tell that P by D is equal to constant. Okay, P by D is equal to K, or P is equal to KT, or P is proportional to density. Okay, that means pressure is proportional to density. Okay, when others are constant. Hope you can understand what I am telling. Next we will discuss the graphical representation. Okay, graphical representation of Boyle's law. Graphs. We know that PV is equal to constant. Okay, or we can tell that V is inversely proportional to P. So if we draw a graph along x-axis, if we plot the pressure in atmosphere and here volume in liter, then we will get a curve like this. So here we can easily understand, if we increase the pressure, the volume will decrease. Okay, another curve we can draw, that is 1 by V versus P. So here we are giving that P in atmosphere along the x-axis, and along the y-axis we are putting 1 by V. Units will be liter inverse. So in this case we will get a straight line passing through the origin like this. Okay, and another, that is PV is equal to constant. If we put PV versus P curve, so this one along the x-axis we are putting pressure, and here PV. So this PV, here temperature is fixed and N is also fixed. So at different temperatures we will get different curves. Suppose this one we are getting that it will be parallel. This is constant, parallel to the x-axis. Suppose this one is T1, this one is T2, and this one is T3. So in this case definitely T3 will be greater in temperature, then T2, then T1. So this type of curve we will get. Okay, so these curves are also very important, and numericals also you have to practice. After completing this chapter, we will discuss the numerical, and next day we will discuss the other gas laws like Charles law. Okay, and different laws are there. So today up to this, and next day we will continue this chapter. Thank you.